Hello, everybody. I'm Pedro Valls from Fundação Getulio Vargas, the School of Economics, and it's a great pleasure to start this this webinar. First of all, I would like to thank David, Jurgen, and Jennifer from University of Oxford, and also Eduardo Massad and Cláudio Struchiner from School of Mathematics from Fundação Getulio Vargas in Rio. And first, I'm going to make a small presentation, and after that, I'm going to hand the floor to David, and after that to Jurgen, Eduardo, and Cláudio. I'm waiting for. Okay. Okay. So I'll give some general information, and after that, we are going to have David will present Jurgen from the University of Oxford and also Nuffield College. After Jurgen's presentation, we will have the presentation from the School of Applied Math. In the end, we have some questions and answers. First of all, it's a disclaimer from the Getulio Vargas Foundation. All the manifestations is expressed by the staff members of Getulio Vargas Foundations, in particular guests, represent exclusively their own opinion and thoughts, and don't represent the institution position of FGV. In order to place your questions, you have to go to the following link that's going to appear down in the bottom of the screen as well, which will enable you to put your questions. And after that, I'm going to put forward the questions to the presenters. Each group will have about 30 minutes. And after that, we have the Q&A questions. So the first paper is by Jennifer Castle, York Doornik, and David Hendry. It's a short-term forecast of coronavirus pandemic. And there is a link of the paper over there in the slides. And they use econometrics techniques. In this case, is local average time trend estimation to decompose the target variable, which is the confirmed cases or dead cases. And I use some trend indication saturation, TIS, and autometrics, which is a sort of machine learning technique in order to obtain sparse linear model. So up to here, I understand a little bit of it, but after this slide, it's the models from the people of epidemiology. The first one is Eduardo Massad. The name of his talk is going to be Quantifying, Testing, and Tracking Strategy for COVID-19 in the state of São Paulo. He used a sort of sphere model, and in this graph over here, you'll see the number of deaths between the months of February, March, and going the forecast for August this year. After Eduardo, we are going to have Cláudio Struchiner, also from the School of Applied Math, that's going to talk about household surveys and vaccine trials in the context of COVID-19. And he's going to use this Colbert's model that is a mix between epidemiology models and also some household surveys and also some machine learning techniques. So after both presentations, I'll put some questions for the presenters, and the questions will come from the audience. And I'm going to remind you, please, to put your name in the questions because I could ask you to ask the question by yourself, or I can do it by myself. Okay, I'm going to hand it to David. David, you can't start. You are in mute. Okay, wait a second.
Okay. So thank you, Pedro, for the introduction, and let me add my welcome to everyone who's listening in to our webinar. It's a pleasure to introduce Jurgen for his talk and to thank Pedro and his team for organizing this. With many colleagues, including Mike Clements, Neil Erickson, Graham Meisen, Jenny and Jurgen, among others, we've been researching forecasting for more than 50 years. Initially, by analyzing the properties of forecasts, which was astonishingly rarely done. The forecasts could be made by any method, model, guessing, or whatever. We wanted to see what led to possible forecast errors. When you have an estimated model that doesn't perfectly match the process by which the data are generated, and it faces unexpected shifts, there are more than 20 possible mistakes you can make. But fortunately, only a couple of these really matter for what we call forecast failure, namely a systematic departure between the announced forecasts and the later outcomes. Such systematic departures are incredibly common in economics and epidemiology and other observational disciplines. When abrupt, unanticipated shifts occur, nothing guarantees successful forecasts, not even knowing the in-sample data generation process itself. Consequently, we went on to develop devices to offset as far as possible the three key problems. We call these robust devices as they avoid systematic forecast failures after shifts. The methods used for our COVID-19 forecasts that Jurgen will describe in a moment are a member of that family of robust devices, but tailored to the properties of general pandemic failure. Over to you, Jurgen.
Thank you very much, David. Thank you very much, Pedro. I'm going to talk about the work that Jenny Castle, David Hendry, and myself have been working on for the last 3 months. And the focus is on short-term forecasting of the coronavirus pandemic. Well, I guess it's needless to say that our lives at the moment are dominated by the COVID-19 virus, and our physical and economic well-being is greatly affected. And I expect there'll be a lot of research to do in the near future in the various aspects. So we focused on real-time short-term forecasts for confirmed cases and deaths, which are, because they're real-time, we are not biased by knowledge that has been acquired after the event. So early on, for us at least, March, April, the epicenter was very much in Europe. After that, it shifted to the Americas, and we've also seen a resurgence in the US. So it's not over yet by any stretch. We've been making forecasts on a almost daily basis from the 20th of March onwards, so about more than 3 months now. And at the moment, we do that for about 100 countries and regions. So it doesn't take a huge amount of time to create all these forecasts. It takes about half an hour to download the data, create the results, and upload again, including a quick check. It's mostly automated. Early on, there were often data issues, like countries that suddenly changed names, say, but by now it's all generally very smooth. So this is an outline of our talk. I'll talk about the data and the methods that we use. I'll talk about forecast evaluation. And then I talk about a different form of forecast that we include as well. Again, how that works, and a bit about the evaluation and conclusions at the end. And then we'll hand back to the other speakers and then to Pedro to manage the questions. So as I already said, focus is on cumulative confirmed cases and deaths. We use the Johns Hopkins data set. For a while, the US states disappeared from that, and we switched to the New York Times data, and then we switched back again to the Johns Hopkins data when the New York Times started doing strange thing with their data. Now, there are many issues with the data, and we could talk hours just about the data, but that's not really the focus. We take the data as given, and if you're an economist, you're probably quite used to the data can be bad, but we have to work with what we have. And we'll see there's revisions. There can be negative deaths. Of course, there can't really be, but there can be revisions that mean that a daily count is negative. All these things we need to be able to handle. Now, there's many relevant policy aspects that require forecasting. Just to touch on a few. Earlier on in the pandemic, we want to monitor cases and have forecast to decide on lockdown. Deaths are relevant because they indicate pressure on intensive care units. And after the peak, like the situation in Europe, when things are not growing so rapidly anymore, we still worry about a second peak. And we also worry about localized outbreaks for which it can be useful to have forecasts. Through all this, the availability of data is crucial. And, well, hopefully this will not happen again. But if it does happen again, we really should focus a lot on the data collection and testing that will help the decision making. And that has not always been great through the pandemic up to now. Now, the context of what we're talking about is that, and that's something that David has already touched upon in his introduction, that we do have theoretical models and we need those to understand what is going on. But at the same time, there is a history of simple database devices out forecasting those structural models. That is not just in economics, that is something we've seen in several disciplines. And we see that again now. And the reason is that there are systematic shifts. There are shifts in the distribution that leads to systematic misforecasting because models tend to have a built-in equilibrium to which they like to return. But if that equilibrium has now shifted, the model will try to return to the wrong equilibrium. So this is also relevant for epidemiological models. Those models do, as I said before, have a sound theoretical basis, and they are very useful to understand what has happened, but they may struggle in forecasting, particularly early on in the development of an academic. And we have policy reactions that lead to sudden changes, and the predictions themselves can feed back in these policy decisions. But we also have seen that the reporting of the data on the pandemic is non-stationary and changing rapidly or changing from time to time as well. Well, as David said, he and colleagues, including Jenny and me, have been working on forecasting for quite a while. So we bring some of our techniques here to this problem in the hope that they provide a useful approach in forecasting when we need robust and flexible approach. This is reflected, everything I talk about is on our website. That's at the very center of the bottom of the screen is the link of the website. There are two papers on the website as well that give all the details of the things that I'm talking about today. Well, let's jump ahead and let's see what we've been doing for Brazil. So here you see on a log scale, you see the number of confirmed cases for Brazil and the number of deaths in Brazil. That's I hope you can see that, the gray line that runs through the center, that is the continuous line with, and through that runs the estimated trend line, which may be quite hard to distinguish from the confirmed and cases and deaths. But you also see our forecasts. So every little red line that kind of emerges from the solid line, those are our forecasts. And you see initially forecasting was difficult. And if you perhaps look at the third, say, for example, this one here, the third weekly forecast, so this is from the end of March for confirmed cases in Brazil, you see that we under forecast, but then if you look at the data up to then, there actually is not an unreasonable forecast at that point in time, because there seems a kind of acceleration after that. And forecasting gets better as more data is accumulated. So this is a quick overview of the kind of forecast that we've been making, and also the errors involved in those forecasts. But now let's go back and talk a bit about how these forecasts are constructed. So we've started data collection on the 15th of March. That seems an eternity ago now. It's actually not that long ago. And then started forecasting the next day. So we had to all develop all these things in a very short amount of time. So obviously the data, particularly early on, was changing very rapidly. The UK went in lockdown on the 23rd of March, so a week later than we started. And as an aside, when we talk about dates, they are always given in the year, month, date format. So let's look how the data was at the beginning when we started. Well, we have here, I picked out a few: UK, US, EU, and Italy. Brazil is in there, but Brazil you can't actually see. At this point in time, Brazil is negligible. But then we go one period ahead. We get more data. We see the rapid growth, particularly for the EU. But then the US is overtaking Italy in terms of growth. Brazil, we still can't see. And these are the kind of data that we try to forecast. But you see that there is no single development. It's all countries seem to evolve in country-specific ways. And now you can if you eagle-eyed in the bottom of the graph, you can see the Brazil appearing as well. And the data now, you can, if we just extend the data to where we are now, then you can see that, of course, things have changed a lot. Things have grown very much. In Europe, things have stabilized. In Brazil, there is still very rapid growth. In the US, we saw a kind of slowdown and then an acceleration again at the end. We can also possibly see on the right-hand side that there may well be some seasonality in the data, certainly not something I expected in advance. There's a case of a data revision where there were negative deaths in the EU data. And at the bottom, you can also see that the symbols and the lines don't quite match up. So again, there was a redefinition of, or a change in definition of the data. So what do we do? And Pedro already gave an introduction to the kind of model that we use. We use what we call linear average of time trend estimates, because it makes a nice acronym. And it's actually, to describe it's a fairly simple method. What we do, we divide the data in moving windows. So we just have sliding windows. We saturate each window with all possible linear trends. Then we select those linear trends that matters. And there we really need to use a computer. We use the Autometrics algorithm, which is a machine learning type algorithm. And then we get lots of estimates, and we average these, and that gives us our averaged trend. And we had assumed at the start that there's no seasonality, so that is what we get. Now we work in logs, as you can see at the top, because all the time series start at 0, but once they're cumulative, once they've left 0, they're not going to return to 0, which is why we just add the number 1 to the count. But obviously, if the count is 1,000,000, changing it to 1,000,001 is completely irrelevant. So here's a slightly more formal formulation of the model. So we have very simple linear models with a constant and a trend, which we've always forced in the model. And then we have all these possible trends that we add to the model, and that is then done for each window. but it's done either on the differences or on the second differences, because we need to allow for exponential growth, but we also need to allow for a showdown. And this model in principle is flexible enough, although we do change the model after a peak has been detected to a saturation with intercepts, but still on the second differences. And then from that, we forecast using a method. So we don't use these estimated trends to forecast, because that would create a very noisy forecast, but we use our so-called CART methods, calibrated average of rho and delta, for creating forecasts. And that's a method that is very robust and tries to make sure that the trend is not wildly over or under estimated. Then effectively we produce a lot of forecasts and we average of those. So initially we use one model and we create forecasts, but then we also use another model and go further back, which gives us 8 forecasts, and we look at the average of those 8 forecasts as well. And as I've already mentioned, once the peak is reached, we change the model somewhat. We only produce 4 forecasts and average over those. But maybe, as I already said, the information is on our website, but I will give an example that may be helpful too. So here is the data for the UK. This is going a while back to mid-April. We have the actual data again in the solid line. And then we produce, because this is after the peak, we estimated the peak to be on the 10th of April. We have 4 forecasts that we produce. So the most recent one, but also going 1 step and then 2 steps and 3 steps back. Then the last one of these, the red line, is our official forecast, and that we report with 80% confidence intervals, but we also report the average of all 4 forecasts, and that's in the black line. So the movement from this average to the red line, from the black line to the red line, gives some indication how things have been changing over the last few days. And really, we talk about days, and when there's exponential growth, a week actually is really quite a long time. And then afterwards, as it's done here in the light blue line, we can add the actual outcomes to the graph, and we can see how well we did. So here we over forecasted in this particular example. Now, one case we're making, and we have various examples of that, is that we want our models to be robust, we re-estimate them, we reproduce forecasts at least 4 times a week, and we want them to be adjust when the situation changes. So here we have the case for Italy in the very beginning of March, where there was clearly a break in the trend of the deaths in Italy. So suddenly it was accelerating, and our model at that point in time, starting just before that, is not picking that up, and that is of course to be expected. But if we then go 1 step forward, you see that the model in the red line, the forecast, does pick up this change in the trend, and of course the black line, which is the average going back in this case, still for observations as well, the black line is not adjusting yet, because that takes longer. But then we go further ahead. Oops, I went the wrong way, sorry. The difference between the red line and the blue line starts disappearing again. Okay, and then we can of course evaluate in many ways. One way is to compare it with epidemiological models. Well, in the next talk, there are 2 different types of epidemiological models presented. I will not go into any detail here, but we've probably all learned a lot more about these models in the last few months, and many of these models are SIR type models or compartmental models, but as I said, hopefully you've been to several presentations about these types of models already. But the focus here now is to do a comparison. How well does our forecast do compared to some of these other models? And then in this case, we have a comparison with the MRC Center for Global Infectious Disease Analysis at Imperial College, which started forecasting about a month after us, producing weekly forecasts of deaths. So just 1 week ahead. And if we look at the mean absolute error of our forecasts and the Imperial College forecast, which is given in the table, you see that for the first half of April, when our mean absolute error was about 600, between 600 and 700, the Imperial College one was closer to 1100. The week later, ours was not very changed, but the Imperial College one was now about 3 times as big as our forecast. But after that, things settled down, and since then, there is not much between it. And more recently, it's probably fair to say that the Imperial College model is slightly better than ours, but things have stabilized a lot more now. So that shows that there certainly is some value in the type of forecasting that we do. And if we express it as the percentage error in that week when things were really bad, our percentage error was about 16% of the total, whereas the absolute percentage error of the Imperial College was about 42%. The bias is also smaller. If we look at the mean percentage error, that we see that our model is less biased than the Imperial College model. So the next topic is estimating the peak, because we do change our specification of the model when there's a peak. So we need to have some method to do this. Well, here we see the experience of China, but the smooth trend in the top left that we estimated for cumulative confirmed counts in China, and at the bottom left for deaths. Then we look at the daily change, and you see in the solid red line the change in the smooth trend, and that is what we use to see if a peak has happened. So not the actual counts, which is in vague gray, because that is really very noisy when we start to look at it at the daily level. And this we use to produce tables of the peak in different countries. And well, again, you can go to our website. What is interesting is the case of the US. So in mid-April, the peak was re-established was the 16th of April. A month later, it was, well, because the data had been revised a little bit, it had changed to the 9th of April. So that seemed very stable. But now, a month later again, that peak has disappeared. And that, of course, is the acceleration that we've seen in earlier graphs as well. So that is unfortunate. And if I would do the same graph for Brazil, then you see again on the left, you see the confirmed cases, cumulative, and the trends. Well, you can't distinguish the outcome and the trend on this scale. But once we look at the daily changes, you see on the right, in red, the result from smoothing, and it just shows that you really need to do a lot of smoothing to get some idea of what's going on from day to day. There's also, in this case, seems to be quite clear seasonality at the weekly level, although at the end that breaks down. So there may be a reason that's something we haven't done, but maybe we should do in a future revision of the model, allow for seasonality in our models. It's not in Brazil, it's also in Sweden and many other countries, that there is strong seasonality, which is most likely related to to how data is reported. And so it's not actually that the mortality is seasonal, although that would be possible as well, but it's more likely that the data collection is seasonal. So we see in Brazil for deaths that there's, rather than a peak, there seems to be a plateau. The confirmed cases has been generally going up, but hopefully, perhaps we may be at a peak now, but really we need to wait a bit longer to decide about that. But once again, the actual daily data are really a bit too noisy to look at that. Well, as the final topic, there's something else that we have in our forecast, which is based on scenarios. But when we started, the only scenario that was somewhat relevant that we had was the experience of China. Now here we see the what happened in China after very heavy smoothing for counts and deaths, for cases and deaths. But also what we did is we stretched this because the China pandemic was on a quite a tight time scale, which may not be relevant for many of the other countries we looked at. So we have stretched scenarios as well. And this then leads to what we call path indicator saturation. So we have all these scenarios at different points in time. We saturate the model with all these scenarios within a certain window of lag lengths, but for the full sample, we select from those what matters. So that's a similar issue as before. We use autometrics for selection, and then we use the automated model to forecast. So at the end, we just have a linear model, and we can use the future of past scenarios to forecast. So we have a very simple forecasting methods. So the models that we estimate are as given there. So we have the 4 different versions of the scenarios, which lagged between A and B, and that is something that is done in a more heuristic way. As I said, this is a very different approach, but it leads to a useful forecast. It's also different from other saturation methods because it very much focuses on something that we can use out of sample as well. And then in our graphs, you see in the purple lines, you see the scenario forecast that we make. So for deaths after the peak in many countries, that seems to work very well, slightly better than the other methods. Again, we produce a lot of paths going back and then average over these paths. So that is all the gray lines that you see. And so the purple line is the average of all the gray lines. And we also produce confidence intervals for these forecasts. Well, just to give a brief explanation of why this can work, look at the graph here. So we have established the peak, and when we have established the peak, we can standardize all the data by the peak. First of all, we can move all the different outcomes to center them on the peak. Then, of course, we still need to standardize the data, and we don't standardize by population because there's still a huge variation between countries, even when you standardize by population. But what we do, we just standardize by the size of the peak, and then you get the kind of graph that is shown here. So in black is the average, what has happened in 8 European countries after standardizations for deaths and confirmed. And you see that these are really fairly similar. And then in the green and blue, light green and light blue colors, you see the same for the scenarios, in this case, China deaths and China confirmed. And you can now understand why these scenarios can be useful for forecasting, because if we go to the right-hand side of the graph, we don't have the future yet of the black lines, but we do have the future of the light blue and light green lines. So this is a promising approach. It's still something that clearly needs further development, because by now we could use other countries as scenarios as well. It may not work quite as well for the countries where we see these plateaus rather than peaks, but it's certainly a helpful method. And if we do, again, a forecast evaluation and compare it to our forecast F, the red lines, and our forecast called average, the black lines, then we see that the mean absolute percentage errors average over, in this case, almost 1,000 forecasts is competitive with F, and as we go further out, seems to be a little bit better. So, to conclude, well, we need forecasts to help us inform about decision-making and planning. As I've already said, we also, to make the forecast, we need the data in the first place. But that's not something we can do as forecasters, as econometricians, but we can, of course, build models for forecasting. And we've used our experience to build models that are a complement to the epidemiological models, models that can come online more quickly and are much more quickly to run. And these then can provide timely and forecasts that are also easily extended to new situations. It's in real time, and of course, it's open for inspection. That's very important, because we do need to find out afterwards how useful this was. Robustness to data issues has been an important aspect for us, as I already mentioned. Some countries, if you look at our website, you will see that for some countries, the data is really very, very noisy, with occasional standstills and then a sudden catch-up and negative counts as well. So in the early phase of the pandemic, our forecasts were clearly better than the epidemiological models. That distinction has disappeared again by now, and it's probably that the epidemiological models are better now in the final stages of the epidemic. We don't learn from models estimates of R. There are no structural parameters that are estimated. That is the purpose of these epidemiological models. So for more information, you can go to our websites and the two papers. And to end with a graph again, I have the same graph for Brazil that I started with, but now the time span is slightly shortened because I've added two other epidemiological models, the Los Alamos model and the IHME model forecasts. Well, I hope you can see it, but the green lines are quite clearly to see. The red lines again are our forecasts. The green lines are the Los Alamos, the Lanel model forecast. And you see that for Brazil, that probably for May, our forecasts were better than the Lanel forecasts, although this, of course, picks out just a few of the paths. And going then towards June, possibly there really isn't much to choose between the two forecasts. In the IHME, so many forecasters don't look at confirmed cases, they only look at deaths. I would argue that later on in the pandemic, confirmed cases may well be more important to decide whether we can come out of lockdown or not. The IHME model only includes deaths, but I think that early on there were some issues with the data as reported, so those forecasts don't look quite as good. So that was one step. That was my conclusions plus, and I am now ready to hand back to the next speaker. So Pedro, please take over.
Okay, thank you, Jurgen, for your great presentation. And before handle to Eduardo, I would like to remind the people that are watching the webinar in the YouTube that it's possible to place your questions using this app.slide.do/event/ this name over there, and I will receive your questions over here and I will pass the questions to the presenters. So I would like to give the floor to Eduardo. Please, Eduardo, can you start your presentation, please?
Yes. Can you see me? Is visible? Okay, I assume that it's visible. First of all, I would like to thank Pedro for organizing this webinar, for inviting me. And the ideas I would like to share with you were related to an alternative control strategy against COVID-19, which is testing, tracing, and quarantine the positive ones. So this is the title of my talk. We are going to test our model with data from the state of São Paulo. The state of São Paulo is the most affected of Brazil. It's a 44 million population size. It's the largest of Brazil, of the country in terms of population size. And it is where the epidemic entered into the country. So the first case of COVID-19 diagnosed in Brazil started in the state of São Paulo on February 27. A patient who arrived infected from Italy at the time. And from then on, the outbreak spread to the rest of the country. As of today, there are 289,000 cases and 50,000 cumulative deaths in the state of São Paulo. And this is an outline of the model that we use. It's an extension of the classic SIR model, in which we have susceptible individuals, exposed pre-symptomatic, infected, and oligosymptomatic, which can remain as oligosymptomatic or can evolve to hospitalized cases or more serious cases in which people need intensive care unit treatment in that. All of them can recover for a new compartment, and we included this strategy of testing the oligo and asymptomatic individuals. We can test all of the population, the susceptible ones, and then we quarantine the individuals who results positive to the test in order to control the epidemic, okay? And the model is deterministic, but we included some stochasticity by using distribution for the beta, the contact parameters. These are the equations which governs the model dynamics. The basic reproductive number of this system is given by this equation, in which omega is this largest equation. We calculated that for the state of São Paulo, and the result at the beginning of the outbreak was around 2.4. This is the incidence of the infection calculated from all the contacts, infected people. All of them are infected with different proportions. And if we integrate the incidence, we end up with total number of cases. This is the integral that results in the total number of deaths, and this one for the total people that would eventually be tested against the virus, okay? So, what is the format of this strategy? This test can be simulated. If we simulate the application of, this should be 10,000, sorry, it's not 1,000, it's 10,000 health agents from the program of Primary Health of the State Secretary of Health that should visit the 3 million dwellings in the state of São Paulo. In each dwelling, the agent would interview the inhabitants, questioning who had had any of the symptoms of COVID since the beginning of March, and about who had had contact with any individuals who had a disease in the same period. In case of positive answer, the individual would be tested for the presence of the virus with RT-PCR technique, and in the case of positive, the individual would be quarantined for 14 days. The cost of the strategy was calculated assuming the cost of the test, assuming the price tag of $48 per sample, and the cost of the agent's salary, assuming to be around $1,000 US per month. And the total cost of each simulated strategy will depend on the rate of testing and the total number of testing, as well as the duration of the strategy. Okay? And this is how the model reproduced the actual number. The black dots are actual number for the state of São Paulo. The blue line is the forecasting with the confidence interval of that. For the cumulative deaths, this is the model behavior. It reproduced very well the observed cases. And these are the simulation of the testing. This is the strategy in which every single one of the 44 million dwellers of São Paulo would be tested. And this is the efficacy. The size of the dots represents the rate. So the larger the dot, the larger the rate. And this is the beginning of each one of those possible strategies. And we see the most effective one should have started at April the 1st with the highest rates of testing. And then we would test 44 million of individuals. If we test 44 million and we detect the positive at quarantine, then we end up with an efficacy of 95% in the reduction of number of cases and deaths. And this is the cost. As we see, this would be very costly strategy, almost $3 billion US. And this is how the efficacy of the test with respect to the number of tests needed. We see this is each one of those colored set of dots is when the strategy would have beginning. And we see that the most effective is the one that should have started on April the 1st with a 95% of efficacy in here, and with about 150,000 tests. This is selective testing. Only those who had reported any symptoms of COVID or who had reported any contact with a non-positive individuals. Quarantining them for 14 days, this is the result of the strategy, and this is the cost. As we see, the selective strategy, as expected, is much more, is cheaper than the unselected one. And we see that the most effective one should have started on April the 1st with 95% of efficacy in reducing the number of cases with a cost of around $100 million US. And this is how we can simulate daily testing rates in percentage of people and with respect to the efficacy. You see that as time passes by, these strategies are reducing the efficacy. If we start on 1st of July with the highest testing rate, we end up with slightly above 70% of strategy in controlling the outbreak. You see, if we start on August, July, we'd end up with at most 60% of efficacy. And this, if we compare, just as for compare two different rates of testing, and we see that in terms of the cumulative number of cases in the end of the outbreak, the highest rate, of course, we end up with the least number of infected, cumulative number of cases. You see, with the same number of tests, we achieve a much higher reduction if we increase the rates, the daily rate of testing. So in conclusion, Had the state of São Paulo decided to adopt this strategy on April the 1st, it would have been possible to reduce the total number of cases in 95% at a cost of $2.5 billion for the indiscriminate strategy, but at a much smaller cost of $110 million for the selectively testing strategy, testing just the suspected and contacts of symptomatic cases. So it's possible to reach the same efficacy with a selective testing strategy, provided that we have access to all the 3 million dwellings in the state of São Paulo. And with this, I end my presentation, thanking again for the kind invitation of Pedro.
Okay, so next we are having Cláudio Struchiner from the School of Applied Mathematics, and I'm giving the floor to Cláudio. Cláudio, you have to unmute.
So unmuted now. So what I was saying to myself before is that I thank Pedro for the invitation and the organizers, and that the title of my talk is about household surveys in the vaccine trials. And I think that we are entering in a new stage of the pandemic in which two topics will need a lot of our attention. One is contact tracing, as Eduardo just hinted in his talk, and the other one is about the vaccine trials that we all want to succeed. So in my slides, I have a couple of issues related to vaccine trials and some ideas on how to proceed and make the trials more efficient. So the basic idea is that that we all agree that we have to compare vaccinated to non-vaccinated in order to assess the efficacy of a vaccine. And what probably not most of us realize is that we also need to challenge those individuals, the vaccinated and the non-vaccinated. So this is what I'm trying to represent in my denominators in those two instances. So in the lab, and as the experimental studies are being proposed with volunteers, the experimenter challenges both groups, the vaccinated and the non-vaccinated. But in observational trials, we control just the vaccine allocation that can be random, but we do not control challenge, because nature is responsible for challenging those individuals. And this can be a source of lots of problems that we have to take into account in our assessment of the vaccine efficacy. The second idea that we need to have in mind is that there are basically three mechanisms of action of a vaccine. So vaccine can block infection, and this is represented in this diagram by the blue line. And this is also the mechanisms that most of us have in mind when we think on a vaccine. But a vaccine can also modify disease and block transmission to other susceptible people. So if a vaccine blocks infection, then the other two mechanisms are, of course, guaranteed present. But most of the vaccines are leaky, and so we cannot achieve full efficacy at this stage. And so we also hope the vaccine would modify disease, in which case vaccinated people would present more benign symptoms. But we also hope that a vaccine would block transmission. So if a vaccine just modify disease, this is a vaccine that is good for the individual, but it might not be good for the population. Because in this case, what we would have is asymptomatic people circulating in the population and able to transmit the disease to other susceptible individuals. So all three aspects must be kept in mind. So this is now a slide that describe a typical household survey and the tracing that can be done in this context. So we have an index case, the first orange circle at our left, and this individual can infect other individuals in the same household and also infect individuals in different households, and so the transmission can jump from one household to the other. So color here represents different households, and the dotted lines represent transmission to the that are not considered. So in this case, in this context, we can break down this concept of R in two components. One component is describes transmission within a household, and the other component describes transmission at the community level. And this context is very interesting because it takes into account the source of infection if we are in a vaccine trial. Because, as I said before, nature controls this challenge, but in this context, the individuals that live in the same household as the index case would all be challenged in the same way. And so we could allocate the vaccines in different households and control better this the bias that could come from this source of infection. In this slide, I list now some of the additional challenges that we have to keep in mind in this in those trials when interpreting the results of those trials. So the first one is that this is a disease that follows a course in which a high proportion, or at least a considerable proportion of individuals present mild symptoms and might escape our reporting. The second issue is about the pre-symptomatic transmission, which also makes this contact tracing and following all the individuals a little bit difficult. The second one is the short generation times that accelerates all the process, and the epidemics can actually outrun contact tracing. We are always too late to find those people. The other one are the imperfect tools, because sensitivity and specificity is not 100%. The second one, the next one is the fact that a vaccine would take about 30 days to elicit a neutralizing immune response. So everything that we do now, we have to keep in mind that we have to observe 30 days along the way in order to compare the vaccinated and non-vaccinated individuals when the vaccine is most efficacious. So we need to predict everything 1 month ahead of us. So our model have to describe what's going to happen 30 days later on. The next issue is low prevalence. So most of the cities and most of the places in which prevalence was measured, prevalence is at the level of about 5%, 10%, 25% in Brazil was the highest one. And so this low prevalence, relatively low prevalence, leads to huge sample size. And the last issue, and also extremely important, is the idea of super spreaders and the presence of over dispersion. The idea here is that 10% of the infected people in the current generation are responsible for 8% of the infected people in the subsequent generation. So only 10% of the people is actually doing the job of transmitting the disease. So in the context of a vaccine trial, only those individuals would matter, and all the other individuals, all the other 90% of individuals, since they are not efficient transmitters, they are not informative to the trial. So this is just to give a quick idea of the likelihoods that we have to handle this kind of household effects. So this is a negative binomial likelihood in which the parameters are related to R naught and also to this over dispersion parameter that describes how intense this presence of super spreaders are in this context. So this is one thing that we can rely on in order to plan and design the trials. And finally, this is a diagram of Comorbus. Comorbus is an agent-based model that is being developed by a whole team of people that I'm going to show in the next slide. But the idea is to have a model that would take as input integrated data sets, social, demographic, and bio data sets containing, for example, viral load, immune response, and other biological information like sequences, various sequences, and integrate those data sets in a dynamic that would mimic the transmission in small populations, for example, a favela in Brazil. And in this way, we can try to design our trial, taking into account or trying to address most of the challenges that I mentioned before, Most importantly, this one that we have to plan things 30 days ahead of time. Okay, so with this slide, I end my presentation. I would like now to acknowledge the contribution of researchers from FGV EMAp, with whom I exchanged some of those ideas, Eduardo, Alberto, and Luis, and the team behind the Comorbus, Thiago, Feng, Luis Gustavo, also IMPA, Guilherme, who is the main brain behind Comorbus, and Dan Marquezan, and also the Unicamp team that are contributing to the development of this ABM model. Okay, so I thank you, Pedro, again, and the organizers, and I'm open to questions. Thank you very much.
Thank you. Thanks very much, Cláudio. And we have some questions from the audience. I will start with the first one who placed a question was Marcelo Fernandes, and it's for Doornik. He has two questions. Well, it's really one question. The first one is, what are the MAPEs for Brazil, if they are in logs or in levels? He means historically.
Well, I'm afraid I don't know these numbers by heart. I have computed them, and I may well be able. So I have a table for, because we focused a little bit more on Latin American countries recently, because we had some requests from the Inter-American Development Bank, and so we have separate tables. And I did also include results for Latin American countries. So let me just see if I can find anything and put that on. So I think I do have something, but I need to put the paper on screen. And let me find it. See if I can find it. Where are we? Okay, we get there. These are European countries, Latin American countries. So here are some results for Brazil. And you see that the MAPEs for Brazil of our model for that period, this is average over 1 to 7 days ahead, are about 4%. In this case, this is deaths. The average actually turns out to have better forecasts than our central forecast. But in both cases, it's a little bit smaller, but it's not a big difference with the Lenel model. And then in the next table, you see it by forecast horizon. And again, you see that there are some differences, but they're not very different. But obviously the forecasts deteriorate quite rapidly as the horizon increases, particularly when there's exponential growth. So the uncertainty, at least. So it ranges from 1% at the one step ahead to about 5-6%, 7 steps ahead. So I hope that answers that question, and that there's more tables in the paper on our website, which I update from time to time as well.
Okay. The second question is from Emmanuel Ornelas to you, Doornik. he said that as you said, the time series seems to be country specific. Could that be particularly explained by the fact that they are modeling cases and death by country? And that is another question by Emmanuel Ornelas as well. And country series are an aggregate on local/regional series, which are varying starting points.
Yes, I mean, we treat every country separately. And I think that's for a good reason, because countries are very different at different stages in their different epidemic stages. They collect data in very different ways. They define death, say, in quite different ways. So it's difficult to kind of use the information from one country in another. But it's something we have tried to do with the scenario forecast, where we try to use the experience from China in the scenario forecasts. But I don't know enough about, we look at about 50 countries and 50 states, 50 US states, and even every US state does do things differently. And we don't really know anything about the institutional differences between states and between countries. And we don't really want to go there either, because I think that's something for future research, not for our forecast exercise. And the second question, I don't think I quite... Oh, Pedro, you have to switch your sound on.
Yes, it's the country series are an aggregation of local/regional series, which had varying starting points.
I think that's a very valid point. I mean, a good example is when we look both at the EU and at the EU countries, but of course the EU is in some sense an adding up of different epidemics which peak at different points in time. So ideally, you go at a more local level, which is why we produce all the EU countries separately, but we don't have enough. Well, basically, we don't necessarily have all the regional data. Certainly not when we began. There was not the regional data available, and now there's a lot more regional data. I think within a country there is not such within a country, within most countries, there is not a huge difference between regions, except when you go to big countries like Brazil or to the United States or, for example, China, where there are very big regional differences. Obviously, for a country like the UK, there are regional differences, but I think they are much less important. And the I guess it's probably more an issue for those models that try to estimate an R, where you get an R that is effectively averaged over very many different regions. I think it is less of an issue for our forecasting approach, but it's certainly an issue we need to think about.
Okay, I have one more question for you, Doornik. It's from Lorena Guadalupe Barberia. Her question is, for the US case, I understand that your model were estimated for states versus the entire country. Can you tell us about the fit of the forecasts?
Yes, well, again, it's probably easiest if I refer to the paper that's on our website. I mean, again, we have tables of the mean absolute percentage errors and the absolute percentage errors for our model for the US in aggregate and for the US states. I will have to add that again, there are data issues. Some states, the data are really quite problematic, whereas other states seem to have a much more coherent data collection mechanism. But we do try, we do look at that as well. Basically, anything that we forecasted, we've tried to evaluate as well to get an understanding how big the errors are of our forecasts. I don't know if David or Jenny want to add something to my my answers.
Okay. I have two questions to Eduardo. The first one is from Emanuel Neles from São Paulo School of Economics. And he asked, in the calculation of cost, did you introduce some measure for the cost of quarantine people?
No, there is no indirect costs. I just computed the cost of the test and the cost of the staff to carry out the test itself. So the cost of quarantining people is not included in the model.
I just received another question from Jonathan Matthias, and he said, my God, I saw that you are using beta to put some uncertainty in your deterministic model. Could you create your confidence interval using that?
Yes, the confidence interval was using, we calculate the confidence interval by the variance of the distribution that we assumed for beta. And then we simulated many times, and then we end up with this envelope that we call it.
Okay. And Lorena is asking as well if your paper is available.
The paper is in the written phase. We just start to write down the paper now.
Okay, thanks very much, Eduardo. And I have a question to Cláudio. How costly is to estimate the comorbid model?
In what terms? You mean computational cost?
Computational cost, yes.
Yeah, Guilherme is the brain behind that, and he swears to me that he has some tricks that makes the program runs much faster based on particle physics, because he is actually a physicist, and so he's using all the tricks that the physicists do to run their particle models. And so the basic idea is that he is running the model using density instead of individual particles in the process. Okay, but the idea is to have a very complete ABM replicating also the biological dimensions, like, for example, viral load and incubation period, and take into account all the censorship and truncation that we have in observing this kind of process.
Okay, so that's the end of the questions. I would like to thank...
I have a couple of questions, if I may.
Of course, Doornik.
Well, let me say first that I really enjoy the other two presentations. It's. I mean, 4 months ago, I would not have predicted that I would learn so much about epidemiological models, and it's really been very nice. And I think I really enjoy. It's a nice thing of Pedro to bring us together and talk about our respective models and learn from each other. So I have just some minor questions, really. The first one to Eduardo. The question is, do you assume that the cost of testing is constant when you look at the different time points? Because I imagine they are much cheaper now than they used to be in the beginning. And also, does your model, but maybe you do not want to go there, do you, from your model, have recommendations, not what should have been done in April, but what we should do now? I mean, for example, in the UK, the whole test and trace strategy has kind of collapsed. And there may be things you can advise that we should do sooner rather than later. And then, I don't know if you want to, but do you want me to split it up? This may be easier if I give Eduardo answers first.
Yes. Yes. The intention of all those simulation is a methodological one. So we are not too concerned in applying the really accurate figures in terms of cost. We just took the average cost of the test from the beginning to now. Okay, so we assume it 48 US per test, which is the average of the test around the country. For the second questions, I will not dare to make any recommendation to the UK government. But as far as I understand, the testing and tracing strategy collapsed because, as far as I know, the government was trying to implement something by telephone, calling people around the country and asking whether they had symptoms. Well, maybe this may work in the UK. Certainly would never be the right strategy here. In terms of testing and tracing, asymptomatics or symptomatics people, in order to isolate them, it must be house by house, household by household. So we have to have an army of people visiting all the dwellings in the country and asking people whether they have or not had symptoms before. For Brazil, the intention of the calculation was to demonstrate that this, as an alternative to social distance, is a myth. It's too expensive to do. So it's not feasible to be applied in Brazil. So for us in Brazil, the only remaining strategy is to keep quarantining people. We struggled a lot to try to convince people to enforce a real lockdown. We failed, fair and square. So we are in this in between. We have about 50% of the population quarantined. And that may even explain why we're reaching the plateau that you've shown in your daily rate of deaths in the country. It's amazing. How can we understand that he reaches that plateau? It doesn't go down because you have this open and close the society continuously. So you are oscillating around a steady state of the 1,000 deaths per day, constantly around the clock. So we will end up reaching 2, 3, 4 million cases. I would not be surprised if you end up the outbreak with 100 or 200,000 deaths. That's the reality that we have to face it.
Fantastic, thank you. So Cláudio, if I may, I have again two small questions. It seems that the household is quite an important unit in your model, but do you assume that household composition is a kind of fixed thing? Because it seems that age is a very important factor in this, and households can be hugely different in terms of their age composition. And so the question is, do you take that into account, or does that matter at all? And then the next question, which I'm not really sure that's a fair question, but you mentioned super spreaders, and obviously that's been mentioned a fair amount, but is that purely anecdotal, or is there enough scientific evidence to actually talk about super spreaders in this case?
Okay, thank you very much for the interesting questions. The first one, we can represent those demographic difference using a contact matrix. So this is the usual way of representing the heterogeneity in the composition of the household and also the source of infection, because not all transmission takes place within household. But of course, this is an important component when discussing quarantine at home, okay? Because if individuals in the population have symptoms and we advise them to go home and stay home, then this is a way to keep transmission within households going on. So it might not be a good advice. Okay. The second question is about the super spreaders. So what we have very good evidence of is this over dispersion parameter, and this is not seen only in COVID. So there is this rule of thumb in which 20% of the infected people is responsible for 8% of transmission. So this applies in most diseases. And using COVID data, fitting models to COVID data, what we see is that this rule of thumb is roughly preserved, and it's even stronger than that. It's 10% responsible for 8% of transmission. And there are several explanations for that. So the super spreader can be a biological super spreader, someone that would shed more virus, for example, than other people. The super spreader can be a social super spreader, in the sense that this individual would have a social life, a more active social life, and therefore would transmit more. And this is very well documented in HIV, for example. And there is also the circumstantial, the opportunity super spreader. So they are people like us, professors, researchers that spend most of their time at home, and suddenly they are invited to go to a meeting with hundreds of other people, and on the way they get infected, and for the social circumstance they infect hundreds of individuals. So this is described for other diseases and has also been described, for example, in Brazil, for one of those professors that went to a meeting and transmitted the disease to 50 other people. Okay, so they are very ordinary people in the sense of biology and in the sense of the social life, but they can, in certain circumstances, become a super spreader. Okay, so one comment regarding Eduardo's cost calculation is that contact tracing has to be done in such a massive scale that we have to consider it as a way to boost our economies. Okay, so the side effect of contact tracing is that we would be hiring an army of people, and that we would be buying tests from our industry and also the protection equipment. So it's like one of those basic programs that can boost the economy in an extremely intense way. So I guess this is something that we should keep in our minds in this process.
it would be a kind of Keynesian epidemiology.
Yes, yes.
That's right. Yes. Okay, I would like to thank everybody, the audience as well. First, David, Jurgen, and Jennifer, and also Cláudio and Eduardo for the presentations. I enjoy very much all of them, and thanks very much to everybody. Okay.
Okay.
Bye-bye.
See you. Bye.